When an AI makes a decision, how on earth do we know why? It's so often just a complete black box. Well, today, we're going to pry that box open and take a peek at what the AI is actually thinking.
So check this out. An AI is 91% sure this is a dog. Sounds pretty confident, right? But what if it's not even looking at the dog? What if it's actually focusing on the blades of grass, or maybe that shoe in the corner? If we don't understand its reasoning, that 91% confidence score, well, it doesn't mean a whole lot, does it?
Okay, to really get a handle on this, let's imagine something. Say you've built this absolutely brilliant AI for a pet shop owner, but they're skeptical. They look at you and say, look, I don't care how accurate this thing is, if I can't understand why it's making its calls, that right there is the classic AI black box problem. And today, we're going to solve it for them. All right, so here's the game plan to win over our skeptical friend. First, we're going to show them where the AI is looking. Then, we'll actually visualize what it's thinking. And for the grand finale, we are going to reconstruct a single AI thought from the inside out. Let's dive in.
So the first, most basic question we have to ask is pretty simple. When the AI looks at a picture, which parts of that image are really grabbing its attention?
One pretty quick way to get an answer is by using something called saliency maps. Think of it like this. The technique kind of works backward from the AI's final decision, figuring out which pixels have the biggest influence. What you get is this heat map that shows you the hottest, most important parts of the image. Now, this method is incredibly fast, but honestly, the maps can be a bit messy, a little hard to read with real precision. For a much cleaner, more precise answer, we can turn to a method called occlusion sensitivity. And this one is really clever. Instead of working backward, we just start covering up different parts of the image with a little gray square, and we rerun the classification every single time.
Okay, so here's how we do it step by step. We take a little gray square and we place it over one tiny patch of the image. Then we ask the AI, okay, what do you see now? And we write down its confidence score. Then we just do it again. We slide the square over, and again, until we've covered every single part of the picture. And at the end, we build a new map that shows us exactly where covering up the image caused the biggest confidence drop. Those spots, that's exactly what the AI is focusing on.
And you know what? This technique can dig up some really weird stuff. In this classic example, researchers were testing an AI on a picture of an Afghan hound. Now, when they covered the dog's face, the AI's confidence dropped. That makes sense. But, and this is the crazy part, when they covered the human's face in the background, the AI's confidence that it was seeing a dog actually went up. It showed the AI was getting totally confused by the person.
So at the end of the day, it's a trade-off, right? Saliency maps give you a super fast but kind of rough idea. Occlusion sensitivity, on the other hand, gives you a very precise answer. It just takes a whole lot longer to get it.
Okay, so our pet shop owner, they're impressed. But now they've got an even deeper question for us. They're saying, okay, fine, I see where it's looking, but what's its mental picture? What is the AI's core concept of a flamingo or a dumbbell?
To figure this out, we use this fascinating technique called gradient descent. We start with a completely random, noisy image, like old-school TV static. Then we basically ask the AI, hey, can you tweak this image just a tiny bit to make it look more like a flamingo? And we just keep repeating that little nudge thousands and thousands of times. And slowly, out of all that noise, the AI's ideal concept of a flamingo begins to appear.
But the results? Well, they are just fascinatingly weird. When we asked an AI to create its ultimate flamingo image, it didn't create one single perfect bird. Oh no, it created this, a swirling image filled with flamingo parts. You see, to the AI's logic, if one flamingo is good, well then 10 flamingos must be 10 times more flamingo-y.
And this other example shows a huge problem. We asked it to generate a dumbbell, and it spit out an image of a dumbbell with a disembodied arm holding it. And you gotta ask, why on earth would it do that? Well, it's because in all of its training data, it almost never saw a dumbbell just sitting by itself. It learned the context, the arm, not the object itself.
And that is the really big takeaway here. These kinds of visualizations prove that AI doesn't think in abstract concepts the way we do. It's just learning a whole bunch of statistical patterns, textures, and yeah, a lot of context. By seeing its thoughts, we can find these hidden biases and actually start debugging our models.
All right, for the grand finale, the final trick to convince our pet shop owner, we are going for the ultimate zoom in. What if we could pick out just one single neuron deep inside the AI's brain and see exactly what visual pattern it's been trained to find?
See, deep inside the network, a feature like a dog's ear isn't a picture at all. It's literally just a grid of numbers in a spreadsheet, a bunch of activation scores. To you and me, it's completely meaningless. But what if we could translate it back into something we can see?
Well, it turns out we can. There's this amazing technique called deconvolution, and it lets us mathematically run the entire network in reverse. We take that abstract grid of numbers and we reconstruct it all the way back into the visual pattern that caused it. And in this case, we get a perfectly clear image of a dog's ear.
The high-level idea behind this is just so cool. We find a single neuron that's firing really strongly, deep inside the network. Then we zero out all of its neighbors, basically isolating its signal. And from there, we just run the whole network backward. We unpool to get the size back, we deconvolve to get the pattern back, literally reversing every single step, until we're all the way back at the beginning. And the image that comes out, it's the exact visual pattern that one single neuron is built to detect.
So there you have it. We've shown our pet shop owner where the AI looks, what it thinks, and we've even reconstructed a single thought. But this is way more than just a cool party trick. This is absolutely fundamental to building AI that we can actually trust.
And look, cracking open this black box is so important for a few key reasons. First, it lets us debug our models when they go wrong, like finding that dumbbell arm problem. Second, it helps us make sure our models are fair by checking for hidden biases they might have picked up. And third, it is absolutely essential in high-stakes fields like medicine or self-driving cars, where we have to be able to verify every single decision.
And with that, our pet shop owner, they're finally convinced. And they don't need to understand a single line of code or any of the crazy math. We built trust, not by showing them performance charts, but by making the AI's hidden thinking process something they could actually see and understand.
Which of course leaves us with one last massive question. We have the tools now. We can open the black box and peer into a truly non-human intelligence. But now that we can finally look inside, are we really prepared for what we're going to find in there? For how strange, how biased, and how truly alien these minds actually are?